Proximity probes, or eddy current probes, are used to protect some of the world's most critical equipment like gas and steam turbines from vibration issues. These systems rely upon precise cable lengths, and so does the machinery protection system. The machinery protection system is relying upon a 200 millivolt per mil or 7.87 millivolt per micron output from the proximity probe. Mismatched cabling or incorrect cable lengths can significantly throw this dynamic output, which causes false trips, false alarms, or late alarms and catastrophic failure. Hi, my name is Mike Scott, Industrial Product Manager with the Modal Shop, a calibration leader for over 20 years. And in this video, I'm going to show you how our Model 9110D portable vibration calibrator can be used to troubleshoot these issues. And I'm also going to show you how relying solely upon gap voltage can be misleading and cause to increase error in the dynamic output. In our test setup, I have our Model 9110 portable vibration calibrator. I've also mounted a proximity probe inside of our proximity probe mounting adapter. My proximity probe is a 5-meter system with 1 meter of integral cable and 4 meters of extension cable located back here. And I also have my proximeter. In this demonstration, I'll be using this digital voltmeter to essentially simulate the gap voltage button that you might find on the front of your data acquisition system. But the digital voltmeter is not required for practical use of the product in the field. The first thing I want to do when calibrating a proximity probe or installing a proximity probe is make sure my gap voltage is correct. And you'll see when I turn on the voltmeter that my gap voltage is at -9 volts. That means the tip of my proximity probe is 50 mils from the target. The proximity probe is linear from 10 mils to 90 mils, so being 50 mils from the target at the start ensures I'm in the center of my dynamic range. My initial gap voltage is correct, and here on the screen you can see that I'm calibrating my proximity probe with 5 meters of cable in my 5-meter system at 7 mils peak to peak and 3,000 cycles per minute, and my output is 202 millivolts per mil, or in microns, the output is 7.96 millivolts per micron. Both of those values well within tolerance for this 200 millivolt per mil system. You can see how a cabling error can easily occur. This is my 4-meter extension cable, and this is my 4.5-meter extension cable. They're the same color. I've coiled my 4-meter extension cable a little tighter just so I can tell the difference quickly without having to find the model number. But they're the same color and they have the same connections. And this type of mistake upon reinstallation of proximity probes can affect the dynamic output of the sensor. Now I've thrown my system off by connecting a 4.5-meter extension cable to my proximity probe that already has 1 meter of cable. So I'm sending 5.5 meters of cable to a 5-meter system. And you can see, calibrating at the exact same displacement, 7 mils peak to peak and 3,000 CPM, I'm at about 177 millivolts per mil. Or in microns, the output is 6.96 millivolts per micron. Here's where relying upon gap voltage can actually cause increased dynamic output error. You see that my incorrect system here with 5.5 meters of cable has caused the gap voltage to drop to -7.9 volts. It started at -9 volts. So if I walk up to my data acquisition system and press the gap voltage button, it's going to tell me that my gap voltage is a little low. What occurs is the technician may think that the proximity probe is installed incorrectly and actually change the distance, or seemingly change the distance of the probe tip from the center of the shaft, when this is not the problem at all. The problem's been caused by the incorrect cabling. So I can make my gap voltage look correct at -9 volts by moving the proximity probe, in this case, a little bit further away from the target. And that's going to cause our dynamic output to change even more. You can see now that I've corrected my gap voltage and mistakenly changed the position of the proximity probe, my output has dropped even further to 170 millivolts per mil, or in microns, an output of 6.68 millivolts per micron. Remember, my vibration protection system is expecting 200 millivolts per mil, so this is certainly going to throw my alert and alarm levels. So now you can see how the Modal Shop portable vibration calibrator can troubleshoot proximity probe cabling issues that sometimes gap voltage can't detect. Not only is it a great troubleshooting tool, it's easy to use. The proximity probe needs to be mounted only once. The exact displacement can be read on the display, and the exact speed of the machine can be simulated by changing the cycles per minute or the frequency in hertz. It's also a very accurate product with the best accuracy in displacement of any product of its kind, and it comes with an ISO 17025 accredited calibration certificate, the only product in the industry to come with such an accreditation. Thank you so much for watching. If you'd like more information on how the proximity probe is mounted, you can watch our mounting video by clicking on the link you see here or visiting our video vault. We also have videos on how to create calibration certificates for both linearity and frequency response for your proximity probes. And we have many other videos on the product as it calibrates sensors used for acceleration and velocity. So accelerometers, velometers, impact detectors, 4 to 20 milliamp sensors can all be calibrated with this device. Thanks again for watching. For more information, please email us at info@modalshop.com.